Well, hi. Sorry for the hiccup. So that thing was something that shouldn't have been there. So yeah, yes. So finally we can join the session. Sorry, we can start the session now. So it's like the third week, and we'll be starting soon. Yes. Okay. Um, I guess since we just started now, we'll wait for a couple of minutes, say like 5-10 minutes-ish, and then we'll start the session so that everyone can shift from the previous link to this link and we'll start it. Kindly wait for 5 or 10 minutes. Yes, Sumit.
Yes, good evening.
Yeah, you have something to say?
No, man.
Speak. Oh, okay, okay. So I was just waiting for 10 minutes since we shifted from one link to another link. So that's why for all of us to join. Soon when people starts joining and we'll continue the session. So in between the session, I won't have to again join people again and again. So just 2 more minutes and then we'll start.
Okay.
Well, I suppose we can start now. So hello everyone. So it's like third week and the third session. So we are close to it's like almost first quarter of the 12-week course. And I guess you can hang on, everything will go on well. You'll get a bit of it. So now I guess as we have seen is like as you all might have also gone through the links and that we have a bit of more theory now and less of the numerical or sorry the practical part of it, so the Python part of it. But we want theory to play a role, that's why we are having to get it's like visiting the theory first and then the how to implement the same thing in Python next. So same things we'll be doing over here. So I'm your TA Jagriti and I'm a third year PhD fellow at IIT Gandhinagar. My work is in quantitative ultrasound, that is for tissue characterization. So basically to delineate the tumor margins from the normal tissue using some parameters of ultrasound that will help us know about the effective scatter size of the cellular structures, the heterogeneity, vascularity, and all those things. So for today's session, we'll first directly start with implementation. So last session, we saw different types of probability and what distributions are there. So we'll just have a quick, not a quick, but a brief look into how should we implement all of those sames in, let me share my screen, in Python. Okay. So I hope my screen is visible. If anyone of you has something to say, he or she can raise their hand. I'll give you mic access and then later you can ask your query. Okay. So first, I guess I hope my screen is visible. So the first thing over here is that, okay, we import the libraries. Now we saw that it's like there were different types of distributions. One of them was the binomial distribution. Now, how do you know that which particular distribution is a binomial? So for a binomial distribution, you look at the data, look at the possibilities that it is giving to us. So it is like, okay, two possibilities. So you look at the probability, you decide the distribution. So here it's something like, okay, success and failure. So we'll just go through examples. But for this, first we need to import the everything about the distributions is within the stats library of SciPy. So then you need to import the specific libraries over here. As in when we go down, we'll be able to see that how different distributions can also be imported from the SciPy.stats. Okay. So this is the binom that we'll be looking at. So the first example is like a survey found that 65% of they were very satisfied. And then suppose that 25% are samples. Okay, so first we'll just run it. So control enter. Then the next one, this is the markup that I've created over here. And next is the code cell. So then we say that, okay, let's say 25 results true. And then what's the probability that exactly 19 are satisfied with the primary financial institution? So can someone remind what was the very basic difference in between having to find the probability distribution or probability mass function and then later to do this cumulative distribution function? So when we do which one? Yes, you can unmute yourself and say the thing. So the session would be more interactive that way. Okay. Okay, if not, then so let's say that I guess I'll do this over here. So we just know that, okay, for cumulative, it's like, okay, going from bare minimum. So let's say we have something like a data set of 0 to 10. We need to find a probability of 10. When it's like only about 10 or exactly those particular n number of samples, we do probability distribution function or a mass function when we have to find for that particular function. But when it's cumulated, so as the English word says, it's like cumulated from the very beginning. So then if you have to find about for 10, that's a cumulative probability distribution function. What you do is like you find it for 0, 1, 2, 3, and so on and so forth till 10. Whereas probability distribution function is for that particular variable, what's the probability? So how many numbers are there in the bin that will follow if the event has been followed, is like if it's success or if it's a failure. So that is how we find that whether it's a probability mass or probability or cumulative function. Okay. So here, if you see, we are asking about exactly 19 are satisfied. So how normally you do is like you take the binom dot PMF is the function that's probability mass function. Now there are three variables over here. First is your K, next is N, next is P. So K is your X, that's probability X of an event that would be occurring. So we have like exactly 19 would be satisfied. So 19 things that would be there. N is your total sample size. So suppose that 25 samples are there and they hold true. Within those 25 are subset is of 19, and the probability is like they found that 65% were satisfied. So that's like 0.65. So we execute the cell and we get the probability. Now, if you want to do, you can also solve this, but using Python, it's much more easier and you can directly compute it. Next is like if you want to see how this particular distribution looks like, you just import your matplotlib and that particular PLT plot, give a figure and axis, make a subplot of it, or you can directly just define it because here we are not having two different plots in it. And then say, okay, so I have arranged over here, and then it's like, say I had like 26 total number of samples. So I just gave it like 0 to 26, and within those I want to see that particular distribution. So how the distribution would look like. So it's something like this. But if you want to also see or quantify where that particular value would be, you can do something like these lines. So that will also help you differentiate or discriminate that how much width a particular point is having. So it's just something for visualization. So those is nothing but axis dot vertical lines. You can give a transparency level to those values and can change them. So something for visualization. Okay. Next is we say that 6% of the workers in Jackson, so this Mississippi, are unemployed. So in a survey, they found that it's like, okay, in a survey in Jackson, it's like they want to ask us that what's the probability of getting two or fewer unemployed workers on a sample of 20. So this is like now we are looking at something or something less than it or something more than it. So there are two terms in probability. We see at least or we say at most. So at most is like, okay, maximum till that point, and can be from say 0 to x number of point. If we say at least x, so it is like x to n number of, so howsoever it can go from it till the maximum value. So here we have to find the probability of getting two or fewer, so less than two, and then two or less. So it would be 0 plus 1 plus 2. So what do we do in this case? We'll directly find the binom CDF, so that's cumulative distribution function. So what we do is like k equals to 2, total number of sample size, and the probability is given to us. Okay. Now, if the same thing is given for n equals to 20, probability 0.4, and our sample variable is like 10, you can, so you need to calculate it for this particular 10 variable. So what you do is like you then find the probability mass function. So that would be 10, 20, and 0.4. So these were simple functions how to help you discriminating between a PMF as well as a CDF. Okay, now if it's very well known that okay, how we do so, so that was a normal distribution, not a normal, like it's a binomial distribution. So you to get known, okay, if we are using some permutations or combinations, so how to get involved within those variables. Okay, next type of distribution is the Poisson's distribution. So in our first session, someone asked that, okay, how do we know if a particular distribution is Poisson's or not? So Poisson's distribution is like an event which is only dependent on a single parameter. So in I guess in general, if you see, Poisson's distribution is dependent on this. So this is normal SciPy library. So whatever text or content you want on Python and how particular things are being done, you can just go visit this particular SciPy library. It will help you all the functions, libraries, and references on the same. It will also have some mathematical formulas, also import it, how to write. So it will give you some basic details onto it. So first, the SciPy.Poisson. So how it is, like it's only dependent on this particular variable, and how that variable varies is that it's a time dependent constant value. So if we see over here, so it is nothing but we assume that the events are occurring independently and at a constant rate. So that is given to us, that's our assumption. Followed by the assumption, we'll calculate the likelihood that how many times an event is occurring in a fixed interval of whether it's time or whether it's space. Okay. So similarly, how we imported that particular binom there, we'll import the Poissons here. Now for Poissons, we only have two parameters over here. One parameter is like our k, so our x variable. Another parameter is mu, that's nothing but mu, sorry, the mean of the function. So here I just gave some random value, it will give me the answer of it. Now you might be thinking that why each and every time this mp.float64 is coming. So because that's a default way the integers in my system would be displayed. If you are supposed to give them like float 32 or say double or something like that, it will also help you to change those particular parameter settings. Or if you just directly print it, it will also give that things also. Okay, so now if I want to see the distribution, I'll do similarly what we did previously. I'll do Poisson.pmf, plot them. So it's like x comma y, and in the y it will be plotting the distribution values. So if here you see the distribution is something like this, if you also want to add the v lines, you can add the v lines and visualize the distribution more precisely. Okay. So I hope till here no doubts were there. If there are, you can raise your hands. So we'll go towards the numerical then. So now it's like we are told that a person normally visits a bank random. So people normally go on weekday afternoons at an average of 3.2 customers. So that's our like average is like mean is given to us every 4 minutes. So that's the time space that we have. Now, what's the probability of having more than 7 customers in a 4 minute interval? Now you see over something over here that this 4 minute is same. So you don't need to do anything over there. Now what we have is the average, and then what is asked is more than 7 customers. So 4 minute is not at all useful in this particular situation because it's the interval that is just the same. So it's just given to you as a parameter to confuse you throughout the situation. Okay, now we have asked that more than 7. So it's like we can do is like we can compute for 0, 1, 2, 3, 4, 5, 6, and we can subtract that from 1. Or what you can do is like you can compute for 7 itself. Oh, sorry, same thing for that, and you can subtract the quantity of from 1, how we do for complementary probabilities. Okay, so you find the cumulative distribution function till 7, give the mu parameter as mean, more than 7 would be 1 minus the probability, and then print it. Okay, so this is like simple enough. You just have to know what you want to do. So okay, if it's a simple distribution, the question is only giving me some average and it's asking me for a certain particular time or space window that's within a particular defined or fixed window, then it's like a Poisson's distribution. If it's giving in between two different values, it's like a binomial distribution. Okay. Now, same thing, another has asked that, okay, what if that happens, but what's the probability of getting like 10 customers during a 8 minute window interval? Now, what happens over here? Okay, so this is just displayed here. So if we do something like the PMF of k equals to 10, and then now here we are finding for exactly 10 customers, and then it's an 8 minute Oh, well, I guess. Okay, no worries. So what happens is that we see here that the mean is 3.2. If we do this directly, it's not correct because our time window is no longer same. So what we do is like we now have the window of 8-minute interval. So what we do is like we multiply 2 times 3.2. So that
Ma'am, your voice is not coming.
stop my screen sharing. I guess all of you are not able to access your mic. Okay, so this was all about binomial and Poisson's distribution. If you have any doubts, you can let me know, or else we'll go to the uniform distribution. Any doubts? Like how, when, what should be used, or anything within the code. Like there are simple two parameters over here. So if you don't know, we can also go through them. If it's fine with everyone, then can give me a that. Okay, we'll go ahead. Well, I guess no one's saying anything. So I hope it's understandable for everyone, and then we'll go ahead. So the next distribution is something called as uniform distribution. Now, don't confuse in between uniform and normal distribution. Both of them are different over here. So first, what we say that, okay, suppose the time it takes to assemble a plastic module will range from 27 to 39, and they are all uniformly distributed. So describe the distribution. And then it's asked that what's the probability that it will take in between this and this second. So we see that, okay, something is ranging, and they have also told us that it's uniformly distributed. So first, there are two functions. There is one function as range, another function is a range, what we have over here. So range is like a type of list, whereas a range is an array function. Okay, so what we do over here is 27 to 40 and 1. Why? Because now we wanted only a range that was from 27 to 39. So 27 can be our starting point, but towards the end, it ends with an n minus 1. So likely how the index in Python starts from 0. So same way, the indexing, so the last point would be 0, n minus 1. So that's why we did something like 40, so that it will give us like 39. So if we print it, we get all the values from them. Okay. Then what we do is like now we want the uniform distribution over here. So they are uniformly distributed. So we'll import the uniform library. And if we want to see that, okay, what can be the mean of the distribution, suggesting the first loc stands for the location of the distribution from where it starts, and scale is the difference in between the range. Okay. So it's nothing but the difference in between 39 and 27. Okay. So that's 12. So when we do that, okay, we got the mean of 33. Now, what we wanted to, so let's find that, okay, what our question asked us, that what's the probability that it will take in between 30 and 35 seconds. So first what we'll do is like, okay, let's just find it for 30th. So we'll find the cumulative distribution function for the range of 30 to 36, and that's location and 12 that is given to us. So this will give us information of you being within 30 and 35. Okay. So that will find that, okay, so these are all the probabilities. So first is for 30, next 31, 32, 33 till 36. So we got the CDF value. So that's like for 30, it would be just, for 31, it would be 30 plus 31, like that. Now we wanted to find something that is in between 30 and 35. So what should we do over there? So we'll simply subtract the probability, that is nothing but 35 minus the 30th probability. So we'll get the probability in between 30 and 35. That was fine. You all understood this part? Okay. Next question is something like, okay, so the average annual cost for the automobile insurance in US in a recent year was like $691. And suppose they say that it's uniformly distributed. So it's told to us that it's like that. And we have the range format. So what's the standard deviation for this particular distribution? Now, here in this case, even though they have told us the the average of the distribution, let's just try and see if we can compute the final distribution by ourselves or not. So we know the location from where it starts. It will start from 200 and it will end at 1182. So the scale would be difference in between both of them. That's like 982. And you find the mean of the distribution. So mean would be something that will give you this particular. So uniform dot mean. Now what they asked us was the standard deviation of the distribution. So similarly, you'll just it's like replace that particular function from mean to std over here. So you do this, you get 691. 691 was over here and you get the standard deviation. So that's it. So that particular question is solved. Now we come upon the normal distribution. So this was uniform distribution, how particular values were distributed across the range of values. Whereas now we'll look at normal distribution, how that gives us the normal bell-shaped curve, the Gaussian shaped curve, like that. So for normal distribution, it's like norm. So you import norm, binomial. So it will import binom. It was Poisson, so it will import the Poissons. Then it was what other did we look at? So we look at uniform. It was directly uniform. So the library names are like very accessible. If you also don't know, you can go through the SciPy page that I just showed, and you can link them through. Now it's something like normal distribution. So you import norm, you import the library. Now if you just want to see how it looks like, so here I have given like normal.ppf. You might say that what is this ppf over here, and I'm giving a range like 0.01, oops, till 0.99 and by 100. So ppf from 0.01 to 0.99, it means that it will give, this is my ending and starting values. That means that it will give me, so this is the value of the probability from where till where I'll be getting the values, and that would be separated by n number of 100 integers that would be in between those two values. Okay, so it is nothing but it stands for the percent point function, and it's the inverse of CDF. Now I don't know how the inverse of CDF stands, but it's something like that will give you the probability at that particular x point, and that is nothing but within the particular range. So for us, this range was like this. Now if you want to see how it looks like, eventually we'll directly plot the PDF of it. So norm.pdf. So this is how the PDF looks like. Okay. Next, suppose that I have given this value, say value of, so my x variable, the random variable that I'm trying to find the value of about, the mean as well as the standard deviation is something like this. Now I want to find the probability of getting a value that is less than 68. Less than 68 is nothing but we'll find the cumulative distribution function for the particular value. So that will give me like p is equals to 0 till it's like p plus 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 till p is equals to 68. So it's like we'll sum it from I equals to 0 to 68, and that would be the probability cumulative distribution function we have over here. So this norm will have this three variables, that is your random variable, you have the mean over here, and you have a standard deviation over here. Okay, now say you want to get a value that is more than 68. So that would be nothing but 1 minus the same value that you have, something like this. If it's in between both of them, what we'll do is like we'll take a difference in between the value that is 68 and the 63rd value. Okay. Now, next. So there's another question that, okay, they are saying that what's the probability of obtaining a score that's greater than 700 on the test? Say that we have got a mean of 494 and standard deviation of 100. Assume that the scores are normally distributed. Okay, so we have an, we'll find this cumulative, so what we have to find? Okay, greater than 700. So what will we do is over here till 700 we'll find the value. So cumulative distribution till 700 will give the average, will give the standard deviation over here, and more than 700 would be 1 minus the probability till 700. Okay, so that is something like this. Next is what if it's like less 550 or less than it? So that's like at most. So what we do normally directly CDF of 550, 594, sorry, 494 and 100. So we get that value. Now if it's between 300 and 600, how we did previously, we'll take the difference in between both of them. So norm.cdf of 600 and then norm.cdf for 300. Okay. So that is here. Next was, now suppose we want to know, so we go, it's like in last to last lecture, we saw that, okay, how much area within a normal distributed curve for 1 plus or minus standard deviation it stands for, or plus or minus 2 standard deviation it's like. So these are all like the parameters that will help us know what's the area under the curve for this particular standard deviation. Now, if the deviation, oh sorry, if the curve was normally distributed, the parameters were like that. If it wasn't, then we read the Chebyshev's theorem, but where it was like 1 minus 1 by k square. So we also got the value of n, so percentage of the values that are within the curve there. So here, if you want to directly get to know, Python gives you the flexibility for the same. So what you do is like you directly see norm.ppf of this 0.95. So under how many, it's like 95% of your particular value, how much area is there. So the value of which for which the x of random variable is less than it. So it's like 1.644. Now this thing, if you want to find, you can go and cross check your z tables that you have, and from the z tables you'll be able to cross check that okay, this particular value is like that. Now if you, this was for the right side of the curve. Now if you want to find the similar value for the left side of the curve, it would be like 1 minus the probability. Okay. Then we'll look at the hypergeometric function. So last time we saw that, okay, this function was different with respect to the binomial function. It was not similar. There was also an MCQ on the same. So our question is something like, suppose we have, okay, wait, if I have something on this on. Okay. So suppose we have 18 major countries that operate in US, 12 are there in the Silicon Valley, and if three are selected randomly, what's the probability that one or more are also located in the Silicon Valley? So at first we'll just do is like we'll import this hypergeometrical functions or distribution. So that is nothing but hypergeom. Okay. Now how the function for this is, it's like dot SF. Here SF stands for the survival function. So that is nothing but 1 minus your cumulative distribution function. So if you are trying to, so cumulative distribution function is something like that is for at most values. Now if you are trying to find something for at least value, so some x and more than x, so you'll directly get the value using the survival function. But if you are trying to get the at most value, you will have to do 1 minus the subtraction. I hope that's clear. So now how the function for this is, you get the survival function, you have your random variable minus 1, then you have the total population, you have the subsample from which the event are decided, and then you have the sample size of it. What it is? You have the sample size of it. Yes. So how you define it over here is, first what we have been told is one or more than one. So that's like 1 minus 1, that's 0. Then we have the total population, that's 18. Then we have the subpopulation for the event, the sample space to be happened, that's like 3. And then we have the standard deviation. Oh, sorry. Was it the standard deviation? No, sorry, sample size of it, what's there within the particular event that we are looking at. So that's like 12 over here. So then we print the p-value for it. Now this p-value is not that p-value of significance testing, it's just the variable that I have given over here. Okay. Now suppose it's something like, so what we saw over here was one or more. Now if it's something like one or fewer of it. Now what my functions should come over here, the 1 minus value should resemble the value that is presented over here above. Okay, so I'll do it for 0, the same values I'll repeat it, but I'll do the CDF now. So till 0, how much I get? So that's like something a very zeroth value. So I get a 0.0 probability, and if I do 1 minus the probability, I get the same value that's over here. Okay, so that way we can also cross check if the analysis that we are trying to perform, it's also fine or not, or are we within the same path of lines. Okay. Then I guess the last distribution, something over here, is for the exponential distribution. Exponential distribution will tell you that, okay, when a particular distribution is exponential, when you have something in between two things. Okay, so, and one more thing, the mean of the exponential distribution is related to the mean of Poisson's distribution by the inverse relationship. So when this was taught, there might be certain relations or formulas that you need to memorize. I'll say that you need to know that, okay, if what's the formula for mean, standard deviation, for population, for sample, for variance, where you need to account for its degree of freedom, all those things you need to consider. Okay, so you'll have to know those specific things. Okay, so here the question was, they have been involved in a statistical quality control for several years, and as part of the process, parts are randomly selected and tested. Now we have been told that a defective part will occur in a pattern that is Poisson distributed on the average of, so we saw that in Poisson's distribution, we only had average and the kth value for which we need to find the values of about. Okay. Now we have the average of about this for every 20 minutes. So that's a window space during the production runs. Use this information to determine the probability that less than 15 minutes will elapse in between any two defects. So that will give us information that, okay, it's the exponential distribution. Okay. So at first what we'll do is like we'll first find the mean of it. So that is nothing but 1 minus 1 by the mean of the Poisson's distribution. So that is for only the 20 minutes for which the average was reported. Okay. Now we'll first import the library, that is expon. So never do this thing that in each and every cell you are importing the libraries. At first only in the very beginning cell, you import all the libraries over there. It's fine that you don't know that what all libraries would be used. So you import them one by one, one by one, one by one. Okay, so that works well. but don't just import it anywhere wherever you're writing the code. This is just for learning, so okay, it's fine. But proper writing code ethics, it does not look good. So it is nice if you just define all the libraries at the first cell, and then later you continue your code functions. So everything would be sorted and organized, and you know that which particular library has been accessed and when. So that way it's fine. Okay. Then now we want to find the mean over here for this particular distribution, and what we are trying to look at is something that is less than 15 minutes. So then we'll have to match the units over here. So we'll do the mean as nothing but 15 by 20. So that would be a ratio. What we are trying to look at was 15, and the mean of Poisson's and exponential is related by inverse of it. Okay, so 15 by 20 is 0.75. It will match the units. Now, so we are just starting from, and no information has been given, so assume it as 0 and y is equals to x by the scale. So we want to find something as less than 15 minutes. So that will tell us about the cumulative distribution function. So cumulative function we'll use over here, and 0.75 is our mean, location is 0, and mu is our mean. So mean that we initially found. So that's a variable over here which they call it as lambda. Okay, so that is how exponential distribution can be done. So everything about distribution, how to find particular distribution, how to solve this particular smaller problems, something like this would be asked in your exams, where you'll have to give the direct code of it, or you'll have a Python interpreter. You do that, and then you give the values of it. So to solve it, or you'll give it's like you'll have to memorize the formulas or it, but you'll have to know the formulas for a bit, just so that you can also cross check them. You can also match your instincts, okay, if it's working well or not. Okay, so that you don't feel that okay, whatever this is giving and whatever I am writing is 100% true. So don't just be based on that, also try to follow the formula part too. So this was all about the distributions. We saw how to plot them. We saw the binomial, we saw the normal, we saw the uniform distribution, the Poisson's distribution, exponential distribution, and the hypergeometrical distribution. So if there are no doubts ahead, we can go through the theory part of the lecture and then followed by the assignment questions. I'll give you a 5 minute break over here, not 5 minutes, like 2 minutes break, and you can let me know if you have any questions about it. Then we can continue the theoretical part. Okay, so if I have no doubts, we'll start with the theory part of it. I hope you all can speak up when we do the assignment parts. Okay, so I'll share my screen. We'll go to the theory content. So my screen is visible to everyone? You can give me a heads up over here because I won't be knowing if yes or not and if I'm audible also or not. So
Yes, ma'am.
someone, yeah, okay, thanks. So we'll okay. So we know that why we are looking over here and why we are doing this particular lecture and how things work and why data analytics and data analysis needs to be done. The learning objectives from the beginning were like we need to know the importance of the data, and for the same, this particular week we'll be looking at the sampling distributions and so forth. So you need to know that why particular how a particular simple random sample is being described, why it's important, the difference in between descriptive and inferential statistics, the concept of it to determine the mean and standard deviation. Okay. So at first, it's nothing but about the descriptive and inferential statistics. So we know that descriptive is something that, okay, that you represent or you quantify everything in terms. So that's like you collect, present, and describe the data. So all of the descriptive statistics are like you compute the mean of your data, standard deviation, median of the data. So you find the data. But inferential is something that, okay, wait, okay. But inferential is something that you draw a conclusion, you make the decisions that are concerning a population and based on only a certain population. So inferential will, okay, sorry. Will be something like this. So you have a sample statistics that's known of out of the total population. So you have your a subset of the sample population. You know the sample statistics of the sample population, and then you make an inference about the population parameters. So your population parameters are unknown to you. So in this case, it helps us to ponder on the question that why only should we do a sampling? So sampling will help you because it's like less time consuming, it's very lessly costly. Then it in such cases, in some cases, it will give you a statistical good significant result of your data based on sufficient higher precision value of the number of samples that you have. And if it's like a research process that you're going through, so research is normally, so people say it as destructive. I don't like that word. So it's like, okay, it's a ongoing process, or it's like a progressive, a cohort process, so prospective study. So there you don't know what might happen when. So people normally say that, okay, that there was a statistical magic number when you might have seen in the slides, that's like 30 number of samples you want for each and everything. But what if you don't have 30, so you take a subset of it, you just take say 10, or you just say take 5. You test your technology or your methodology on the same, and if it's right and if it works, so it will save your product as well as samples too. So the main population is fine, you're testing on a cohort. Probably in future you can increase your sample sizes, but now you know that if even in a very small cohort it's working well, so why not it would work in a bigger cohort. So that way you will also save this particular products also. And another thing is, if accessing the population is impossible, so the only option that's left to you is the sample. Next, another thing to consider is the census. Why census? So if there is a census kind of thing being taken into consideration, so you'll have to think that you'll have to eliminate all the possibilities that a random sample is not representative of the entire population. So if it is not, like, now it should be representative of the population, so you'll have to eliminate the possibility that it is not representing the population, because you want your sample to be a subset of the population, not the other way around. Okay. Also, if a person who is uncomfortable with the study sample information, that is why a census is mostly useful and needed. Then there are different techniques for sampling, one like random, another is like non-random sampling. So this is like very brief theory that also is discussed in the lecture slides, but just to give you a simple idea that how they differ. So one works on randomness, another works on non-randomness. One has a unit of intersection where a chance is being taken. So you no longer have bias in this particular process. So it's also called as probability sampling. Whereas in the another way, another experience, you have a non-probability sampling. So it is like you have an open selection bias, so everything would be biased what you're trying to do over there, and each and every probability won't have the same probability. Each and every event of or a particular unit won't have the same probability that you're trying to do for a sample. Whereas for random sampling, you take into consideration that every unit of your population has the same probability. Okay. So this was the inferential statistics. Now there are different sampling distributions, and there were like different techniques for this random sampling and non-random samplings. So one was like simple, stratified, systematic, cluster. Each of them have their pros and cons, but eventually they all mean the same thing, that okay, how each and every probability should be same for a particular unit. Then you also have within stratified, it's something that if it's something that represents a sample, that is also a subset of the entire population. So there are two categories to it. One was like proportionate, another was like disproportionate. So proportionate shows that it is proportional to it. Disproportionate shows that it is different from it. Whereas within a particular stratum, your values are like homogeneous. From two different stratums or in between two different stratums, your values are heterogeneous. Okay. Then you do systematic sampling. That's like you take the entire population. Now you know their sample size. So if my entire population is like say 100, my sample size is say like 10. So my k number of values, so at which particular values I'll start doing the sampling is like 10. So say if I start from 200, my sampling would be like 200, 210, 220, 230, and so on. Okay. Next was like cluster sampling, something like that. So cluster sampling, yes, Fazil, go ahead. Yeah, I guess that was by fluke. So cluster sampling was something where you take that your data is not overlapping and you see by what particular plane your data are differentiated. But this is something like now you'll have to consider now if your subset is also part of the entire population, now you sample it again, then you again sample it. So that is like your design number of values, you sample your cluster with respect to your entire population size. Then for it also had its own pros and cons. You can have a look there, but this kind type of questions are something like you just need to know what particular thing is what about. You don't need to memorize them. So you just should know the gist of the entire thing. Okay. Then you have something called as non-random sampling. So there are also terms that okay, if it's by biased by someone, it if someone has a judgment of the same, or if it's based on a referral or a convenience of a particular person. So there are different kind of non-random sampling where each and every unit of the sampling is not equal. Okay. So then you have different sampling distributions. I suppose this sampling distributions are like type of the same, like the sample mean, the sample proportion, and sample variance. Now over here, I've not given particular formulas over for the it's like for every or in everything, because it's like okay, you find the mean, you find the variance, find the standard deviation. Everything is depend if it's a sample for a particular sample population, you take into account the degree of freedom. So that was like you divide it by n minus 1. If it's not, and if it's in between different groups, so then your error would become something like standard error. So that all theory is there in the lecture pretty well good, and I don't want to bore you again with the same stuff. So I've not included it over here. If I find something that is so at first what you do is like you'll develop your sampling distribution, you'll find the mean of the distribution, you'll find the standard deviation of the distribution, and same thing that we did in the last lecture. So you find the z-score, that is like x minus mu by sigma. You find the range in between both of them and you find the probability. That's all everything is about within the sampling distribution. So for this particular section, you'll have to know the formulas very nicely. Again, there were cases that okay, if it's not independent, if it's dependent, so in those cases your formulas will also change. So all those formulas also you'll have to memorize to a bit. Then sampling distribution have their own proper so if someone can say that how the properties of the sampling distribution changes depending upon the sample size. Is your distribution more narrower or broader when your sample size is larger or smaller? You can just unmute yourself and speak up because we'll likely have, say, 10-15 minutes more and then we'll be done for the session. So, assignment questions that will help you solve the next week's assignment and just this small question. So, what happens if your sample size gets larger enough and what happens it's very smaller to the shape of your distribution curve? Someone. Well, guys, I don't know you. You don't know me, so you can just pick up your mic. Cameras also disabled, so you're not showing up your faces. So it's fine. You can just unmute yourself and say the answer for the same. I know that all of you might know about this. Even if you don't, you can ask straightforwardly. Anyone? Well, okay.
Ma'am, for
Yes.
large sample size,
Mhm.
it will happen normal distribution.
Yes. So for a larger sample size, it's like a normally distributed data. For a smaller sample size, your
Yes,
curve
ma'am.
is more steeper. Yes, exactly. So as and when your number of sample size increases, our distribution curve tries to achieve a normal distribution. Okay. I guess the other things that were taught in the class were more likely based on formulas. And that's like, you can go through the formulas part. So everything same there. So we'll go through the assignment questions for the last week so that it will help you solve the assignment that's due tomorrow. Okay. So assignment are. So first question, why one should not go for sampling? Here you'll all have to speak up. I won't give you the answer straightforwardly. Direct. Okay, some why one should not go for sampling. It is less costly, or the person authorizing is comfortable because the research process is sometimes destructive. Well, of course, the process is destructive, then person authorizing is comfortable, but it's less costly. So, are these the reasons that why one should not go for sampling, or are these the reasons that why one should go for sampling? Yes, yes. Answer, answer. No one? Okay, so these are all the reasons why we should go with sampling and not for sampling. So none of the above. Then next, stratified random sampling is a method of selecting a sample in which what happens? The sample is first divided, or various strata are selected, or the population is first divided and then the random samples are drawn from each stratum, or none of the above. What's the answer? Quick, quick.
The sample is first divided into strata.
No. Someone else?
The population is first divided into
Ma'am,
strata and the
population
random
will divide
samples
it.
Yeah,
are from each strata.
the population is divided into strata before we do random sampling.
Yeah, yes. So the population is first divided and then the random samples are drawn from the stratum. Okay. Third question. So it's something that you need to know the formula for the same. If you don't know, I can tell you, but try memorizing if you have gone through the video lectures. So if a true proportion of customers who are below 20 years, the probability of them is like 0.35. So this is something based on from the last week's lecture only. So what's the probability that a sample size of 100 will yield a proportion that has a value in between 0.3 to 0.4? So what you do for this is you find a range of probability values. So you have your z-score, that's like x minus mu by sigma. You have your probability for a particular value. So this is your entire probability. You have your sample size. So what you don't have over here is your standard deviation. So how you compute standard deviation? So if I can tell you, can you tell me the
Ma'am, you are not audible to us.
I'm not audible?
Now you are audible.
Oh, okay. So the question was, if a true proportion of customers who are below 20 years, they have a probability is 0.35. What's the probability if the sample size is 100 in between the population of 0.3 to 0.4? So you know the concept of z-score. So we find x minus mu by sigma. Our x for both of the condition is 0.3 and 0.4. Average is given to us as 0.35. We have the sample size of 100. What we don't have here is sigma. Sigma is the standard deviation. So how do we compute standard deviation? That is like square. So if you all can compute the standard deviation, the sum is like, it's fine. Okay, you can compute the z-scores later from the z-sheets and you can have a look at it. So you can let me know what the standard deviation comes.
Ma'am, 0.04.
Yes. So the standard deviation is 0.048, and then accordingly you can just do like 0.3 minus 0.35 divided by 0.03, so 0.04, less than the z value less than 0.4 minus 0.35 divided by the standard deviation, and then you can compute the ranges from the z table. Okay. Fourth question. So calculate the probability of getting 12 heads in 20 attempts from a fair coin. So you can let me know how should we proceed, and then we can code it like that. So we have the 12 heads, that's a x given, in 20 sample size that's given to us, and a fair coin. A fair coin, so it will have the probability of what? So in a fair coin, what would be the probability?
By 2.
Sorry?
Ma'am, 1/2. Half.
Yes.
1/2.
So in a fair coin, the probability would be like 1/2. So that's like 50%. So I've done the same. So how do we compute them? Would be something like here. So we know that, okay, there's a binomial distribution because we are given two choices, so success and failure. And we have 12 heads, so x is 12, total sample size was 20, and our population was this. So we do binom.pmf, so value at that particular 12th head. So what's the probability? It's like 0.12. Okay. Then next question. Here. Next question is a question paper contains like 90 MCQs. Each is having like 1 mark. There are 4 alternative answers for the same, only out of which one is correct. Mr. X will answer this question randomly without preparation. And what's the probability that he or she gets at least 10 marks? So here at first, The question is at least 10 marks. So what will we compute here? Do we do PMF or do we do PMF, PDF, or do we do CDF? So cumulated function or a probability function, Bayes function, which one? No one? So we'll do a cumulative distribution function because it's like at least. And then we'll compute it for 10 marks and then we'll subtract it for like 10 or more than 10 because cumulative will give us the value for about 10 or less than 10. Okay, now what would be the probability over here? So you can say that. Now we have 4 alternate answers. So 4 alternate answers, so 4 given choices and 1 event only to be the correct one. So what's the probability of a single event to be correct out of the 4 choices? Chalo. What would be the answer? So what would be the probability will? For one particular MCQ to be correct out of 4 alternative answers. No one's saying anything. What happened? Well, okay, the probability would be something like 1 by 4.
0.001.
Right? 0.001.
0.1% of.
So it's like you get a one alternate. So you go for say JEE and then you have 4 options over there. Out of the 4 options, only one option is correct. So your the probability would be number of events likely to be success divided by the total number of events that you have. So 1 by 4, that's 0.25. Okay. And your entire
Okay, ma'am.
population size or sample size over here is 90. So how do we do that is, now we need to find it for at least 10 marks. So what we do is like we'll find the binomial distribution, the CDF. So why binomial? Again, we have one correct, one wrong like that. We'll find it for 9 because 10th is the variable that we want to find it. So at least 10. So we'll first find for 0 to 9 and it's like inclusive 10. So we'll do for 10 and more than 10. So we'll first find it for 10. Oh, sorry, 9. Entire sample size is 90. Your probability is 0.25. And for at least 10 marks, it's like 1 minus the probability of 10 marks. Okay. So your answer is 0.999. Okay. Next question. So similar questions are there, for your this week's assignment. So if you pay attention now, you'll be able to directly solve those questions there. So on average, like items that are supplied by the manufacturer are defective. So 5% of the items are defective. So what does this tell us? That the probability is what? What is the probability over here? So probability is 5%. So that's like 0.05. Okay. Next, it's told to us if a batch of 10 items is inspected, what's the probability that 2 items are defective? So 10 is our entire sample size. X is this particular sample that for which we have to look at it. Okay. So something like binom. So for 2, we have to look at it. 10 is our total size, 0.05. That's like 50%. 5% was our percent deviation. So we got the probability mass function for any 2 items that are defective like that. Okay. So binom.pmf. Okay. This question is next. So I guess last 4 questions we have. So a car distributor in city Y experiences an average of 2.5 cars daily. So now we have average. So something probably can be Poisson's distribution. Let's see. So find the probability that on a randomly selected day, they will sell like 5 cars. So we have got a K, we have an average. So what do we do over there? We find a probability mass function or a cumulative function.
Ma'am, PMF.
Yes, so we do the PMF over here. Someone there? No, right? So what do we do over here? We'll import this Poisson's distribution because it's the average and we have the next variable. So that's exactly the Poisson's distribution and Poisson.pmf would be our answer. Okay, so this is our answer for the same. Next. Next is now what
Ma'am,
if this...
I have a question.
Hi,
Hello,
yeah?
ma'am.
Yes, yes.
I mean, exam hall we should do in Python or we can solve the question in the written.
So either ways, it can be like you'll be given some numerical and you'll have to solve. So that is why I said formulas can be memorized to a bit that you understand them. So some formulas are like self-explainable. You can go through them and it
Yes.
would be like, okay, you don't need to memorize them. It's just as simple as normal that you have studied through 10th and 12th. But something like the sample statistics where you have the degree of freedom concepts, you'll have to see those. But in exam, probably a Python interpreter can be given to you. So those points would be solved when we are
Okay.
like within 10th, 11th week. So you'll be able to know that how the exam format would be like.
Okay, ma'am.
Okay. Next question is if they sell no cars. So that's like exactly zero value that we have over here. So we'll find it for nothing. So k equals to 0 and our mean is like 2.5. So we have the formula for the same. Next is if they sell at most 2 cars. So what do we do over here? For at most 2 cars?
Cumulative.
Yeah, yes. So we'll do a cumulative distribution. So what we do over here is we take a Poisson's distribution cumulated to this. So at most, so we don't need to subtract it from anything. So it's like 0, 1, and 2, and it will help us find the answer to it. Okay. And then the last question is this. So find the probability that on a randomly selected day, they'll sell exactly 1 car. So what do we do over here?
PMF.
Yeah, so we'll do a PMF over there. So that's nothing but our Poissons.pmf k equals to 1 and we have an average of this. So with this, our today's session is done. If you have any queries, you can let me know. You can stay back. I'll be here till like 7:45ish or 8 o'clock. And done. If you have any questions, you can let me know, or else if you're done, then you can also leave. Thank you. So if you have any questions, you can let me know, or else we'll close the session. People who are there in the attendees can let me know if you have any questions. You have something to say? Any questions? So everything that we did today was fine. You all understood the Python part, the theory part. I didn't go much into the theory part because I didn't want it to bore you, and the session was like 6 to 8, so didn't want to extend it also. Because same things are here and there, so I go it again and again through the same stuff like that.
Ma'am, in exam, we have theory and practical question both. Means
Yeah,
the
yes.
theory part and practical means Python program part. Okay.
Yes, probably. I guess they won't ask you to code, but it can be something like,
Okay.
something like this has to be done.
Mathematical
So,
question.
yes. So probably they
Okay.
can also ask that, is this script correct? So do we write something? So if we have to find something like
Okay.
this, so is the script for this is appropriate or not? So probably chunks of code can also be given for you, or to expect the output from the same. So something like that can also be there. So some component can be there.
Okay, ma'am.
Any questions? Like, we have a couple of people over here. So if there are no further questions, then you can also go around and join the other TA's session. That session is from 7 to 9. It's a Google Meet. So the same thing is there on the announcement page. You can join there and have a look at, like, he'll also be teaching Python. So same thing about this week, but probably he's more into Python. So if you want to learn basic function and arrays and dictionaries and libraries, so probably that is like there also you can invest some of your time. Okay, so I feel we don't have any questions now. So we'll close the session for today. And thank you for joining. We'll see you all in next week's session. That's next Tuesday, coming up week's Tuesday. Okay, thank you. Bye-bye.
Thank you, ma'am. Thank you, ma'am.
Thank you.
Thank you, ma'am. Bye bye.
Thank you. Bye-bye.
Thank you so much, ma'am.
Thank you.